We left off yesterday with some of the stuff. Talk about exponential functions. Remember, by definition, an exponential function is a function, or we think about it as an equation, where the variable is located in an exponent. Okay? So we left off yesterday with the statement something like all exponential functions are going to be of the form f of x equals a to the x. Okay? This a is called your base. Okay? Now, what we can do with that eventually, just like what we can do with any other equation, is that we can multiply it by something out in front. Okay? We can add or subtract stuff here. We can multiply this x by something out front, and we can add and subtract stuff out here. Okay? So we could do a lot to this to change it. What we usually do, and what we're usually interested in an Algebra 2 class, is when it's usually just based on looking at a to the x, but sometimes we'll put a number out here in front. Okay? So maybe put like a 2 out in front or a 3 or something like that. Okay? So that's kind of what I want to talk about here as we move on today a little bit. But I want to graph a very simple exponential, and hopefully we can draw some conclusions to help us graph these things. Okay? So the first way we're going to draw this and graph this is just how you've been introduced to every single new graph since algebra 1. Okay, since maybe in 7th and 8th grade. The way that we've introduced new graphs every single time has been to take and develop a chart, say these are the x values that I'm going to use, and then these are the y values that come back. Okay? So I'm going to start my chart, and we're going to start it down here. I'm going to go about halfway down, and I'll put a 0. Basically what I want to do here is I want to show some values that are to the right of 0 and some values to the left of 0. So let's start with 0. If I plug 0 in here, so it's gonna look like 3 to the 0 power. Does anybody remember what 3 to the 0 power is? It is 1. Okay? So when x is 0, y is 1. Okay? Let's try an x value of 1. Because I want this to be in order here and when we're done. When I have an x value of 1, it's 3 to the first. What is 3 to the first equal to? 3. Okay? So you get 1 comma 3. When I plug 2 in, what's 3 squared? 9. Okay? Now, I can keep going, but if we look at our chart here, and this is what happens with exponentials quite a bit, is that you quickly run out of room. Because when I go 3 cubed, that turns into 27, and now I've got double or triple the size of my y-axis to get there. Does that make sense? So I'm going to stop there with those. So those are values to the right of 0. So those are x values I'm choosing that are over here. I want to choose x values that are over here now. So negative 1 makes sense, right? Okay. Now, do you guys remember what we do when we have a negative exponent? I have to flip it. So right now, this is 3 to the negative 1 over 1, right? So what we do is we take that 3 and we put it down here, and now the exponent becomes positive. When that moved, there was nothing left up top. So you leave a 1 up top. And it gives me 1 over 3 to the first, which is just 1/3. Does that make sense? Okay. Then we'll have 3 to the negative 2 when I try x to be negative 2. I end up doing the same thing. Now I put a 1 up top, and this 3 to the negative 2 goes down here as 3 squared. So what's 1 over 3 squared? What's 3 squared the same as? 9. Good. So I get 1 over 9. All right, so what that does for us is it gives us these ordered pairs now that we can plot, right? If I go -2, 1/9, that's going to be really hard to graph here because I have to come over here to -2, and now I got to split this up into 9 sections and find that first one. So it's a very small value. So maybe it's like right there. It's probably even closer or lower than that, but I got to approximate. Okay. If we go -1, 1/3, then I'm at an x value of -1, and that would be about 1/3 of the way up to 1, right? Does that make sense? Okay, so there's that point. The other ones are going to be easier to graph. These ones that are negative are always hard to graph because they're fractions. 0, 1, that's easy. So 0, 1 is right there. 1, 3, again, easy. Right there. And then 2, 9 up there. And just like what we've always done in Algebra 1, 8th grade math, whatever it may be, I now connect those, right? The smooth curve. So that's what our exponential graph for 3x looks like. Now, I'm going to go to Desmos here real quick to show you that cleaned up. And I think I've shown you this before, but if I want to, in Desmos, make a table, okay, using what we just did, if we go negative, x was -2, and go 1/9, and then -1, and type in 1/3, 0, type in 1, or sorry, I guess it would be, yeah, 0, 1, then go 1, type in 3, 2, and 9. Are those points there? And then this is just eliminates the human aspect of things. These points, you know, now I didn't have to guess where 1/9 was, right? It automatically puts it where it should go. Okay, same thing here. But we see those are the exact same points that we graphed by hand. So now if I put, I'm gonna go f of x equals 3 to the x. That's the graph, right? Okay. Now it's a smooth graph. It's something I want to talk about here real quick. Let's go down here to like -20. Okay. If x was -20, we'd actually have 3 raised to the -20th. Okay. That number is very. Anybody remember how scientific notation works? How does that number right there tell me what I've got? What does 2.8 times 10 to the -10th really mean? Tell me how small it is. It's telling me, so that -10 as the exponent tells me the number that we're really talking about here, we take the 2.8 number that's out in front and we move the decimal spot 10 spots to the left. So what we would have here is we have a decimal, 9 zeros, and then a 2, 8, 6, 7, 9. Okay, does that make sense? That would be the y value when x is -20. Is everybody okay with that? Is that a very small number? Okay, let me try this real quick. Let's go out to x being -50. I get that. So that tells me I have a decimal, 23 zeros, and then a 139. Does that make sense? Is that a pretty small number? Kind of. But is it 0? No. Pretty small though, right? Let's go out to, I can get small, let's go out to 100. That tells me I have a decimal, 47 zeros, followed by a 194. Is that 0? No, it's not, right? So negative 300. You have a decimal, 143 zeros, and then a 7. Is that 0? It's not. Now I put negative 3,000 in, so what we've done here is kind of we've broken Desmos. It's not programmed enough to go. I'm actually kind of interested in seeing where that negative 1,000. Okay, so 500, it lets it calculate to 600. 700, no, but let's go. Okay, so 678. So basically what we're saying here is that as we get to an x value of negative 678, we kind of exceed what Desmos is capable of doing. Does that make sense? Okay. If you're using a TI calculator, one of these, okay, you can do the same thing. I want to show you what happens when we do something like this on TI calculator. So basically I'm asking it to take 2. All right, so it's 3. I just froze everything. All right, so if I take 3 raised to the, we were trying like negative 678, okay? See what it gives. It gives me 0. If I go 3 to, let's go to positive 678, it gives me this. It gives me, so I'm taking 3 and I'm multiplying by itself 678 times. If you ever get an overflow error on your calculator, basically what it's saying is that you have asked for a calculation that is so large that we don't have enough memory to be able to actually calculate it. Does that make sense? Okay, so we kind of break the calculator essentially, or momentarily break it. And that's really what's happening when we do this with very large numbers. But visually, what we're seeing, what does it look like? This red line is the x-axis. So I'm zooming in, right? And it broke. It won't zoom in any further. So let me try. We can do this on, I know GeoGebra will do this for me. So if I go 3 to the x, okay? And just to, does it look like now the green line is the x-axis? Okay? But if I zoom in on that green line far enough, it takes a minute. Ah, broke it again. We'll go back over here a little bit closer here. All right, so it looks about right here that we're touching the x-axis, right? But if I zoom in far enough, are they separate? Does that make sense? So the idea is I should be able to, and this is what that was showing, that when we get like a decimal and then 143 zeros and then like a 129 or something like that, that is demonstrating that I should be able to zoom in no matter where, and there be a gap between the graph and the x-axis. Okay? Because remember what we're doing here, and this is going off of what we talked about recently with negative exponents. If I have 3 to the negative 100, that is 1 divided by 3 to the 100, right? Okay. That means I'm taking 1 and I'm dividing it by a lot of things, right? So let's say I'm taking $1 bill and I'm breaking it up that many times, 3 to the 100 times. Okay. I'm going to have a bunch of very, 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 very small parts, right? Does that make sense to everybody? I'm going to have a bunch of very, 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 very small parts. So what that means then is that I'm going to still have an amount though, right? A non-zero amount. Okay. Think about this. If I had 3 to the negative 2, that becomes 1 over 9. So if I took $1 and broke it up 9 times, each one of those would be a 1/9 of my dollar. I would have very small parts, right? Okay. But if I go 3 to the negative 100th, it is the exact same thing, but those individual parts are much smaller than what they were here, right? But it's still an amount that we physically have. Does that make sense? Okay. So is there a number that I can put down here that I can divide by and get 0? Is there a number that you can do that with? Is there any numbers that you can take any number you want? Any number you want. Start, and it doesn't have to be 1, okay? Could be 2, could be 3, could be anything. Take any number you want and divide it by the biggest number you can imagine. Does it ever give you 0? It does not, okay? And the idea of that is that there will always be, because it's not giving you 0, and the distance that we're talking about here, that 1/9 that I'm getting there with 3 to the negative 2, that 1/9 is ultimately, when we look at the 3 and negative 2, the 1/9 is this distance right here. Does that make sense? Okay. If I go 3 to the negative 3, I would have 1 over 27. That 1/27th is that distance right there. Okay. So if I go 3 to the negative 100, or 1 over 3 to 100th, this number, whatever it turns out to be, will be, when I get down to the x value of 100, it will be that distance between the green curve and the x-axis, right? So we're saying that this quotient can never be 0. So what I'm telling you here then is that there is always, no matter what x value you choose, there is always a gap between the x-axis and the graph. Does that make sense to everybody? Okay. And that's what I was going to show you as I move over here and now zoom in on like negative 8. If I zoom in on negative 8, eventually you see the gap, right? Okay. Even though when I'm standard view, it looks like they're the same. Looks like the x-axis and that line are the same. See if I could go to negative 20. See if we can zoom in and see if there's a gap. And the thing with some of these calculators, GeoGebra is better than Desmos, but eventually I get zoomed in so far that it breaks it and it makes things disappear. Okay, Desmos just like the level of zoom that I'm allowed to go on Desmos doesn't go far enough to see the gap. But there's always a gap between the green curve. So no matter what, as far as I want to go out here, okay, if I could zoom in right here on that right there, there's a gap between the x-axis and the green curve. Does that make sense? That zooming that we're doing, that's a calculus concept. We can always zoom in on a section an infinite amount of times and see the behavior that's happening in that zoomed in window. The reason I talk about that in that amount of detail is because that relationship has a name. Okay? What we say is that the x-axis is an asymptote. You ever heard that word before? An asymptote. Okay, good. So an asymptote, okay, is a line on a graph, okay, in which your graph approaches but never touches. Does that make sense? Okay. So, and in this case, when the asymptote is horizontal, basically it tells you what happens when your x values get really, really, really big in either the positive or negative direction. Okay. So what is happening to our graph as these x values get really, really, really big in that direction? Our graph is approaching 0, but it never touches 0. Okay. There's always going to be a little bit of gap there, but that as we move further and further to the left, that gap gets smaller and smaller and smaller. Does that make sense? But it will never get to 0. Okay? So if I go out, and this is not something you would do, but if I go out to 3 to negative infinity, if I knew what infinity was, and I was to go out to that value on the x-axis and zoomed in enough, there's going to be a gap between the curve and the x-axis. So the x-axis in this case is called an asymptote. It's a feature in a graph in which your graph approaches but never touches. Okay? In Algebra 2, we talk about horizontal asymptotes, and we can talk about vertical asymptotes, lines that are up and down. We haven't talked about any vertical ones yet. We'll get there eventually towards the end of the year. But the x-axis here is an asymptote. And while I'm talking about this, is every single exponential function, okay, that we come across early on here is going to have the x-axis as an asymptote. Okay? Question, Maya? So so when I'm zooming in like this, so that takes some time to get back to that. So you see how it's changing when I'm zooming in, it's changing the decimal part. Okay. Eventually, because I zoom in so far, that this E2 is basically telling me that the degree, it's scientific notation. E represents times 10. So it's telling me basically negative 1.3008 times 10 to the second there. That's what that's doing. So don't worry too much about that. It's just the notation that GeoGebra uses. You don't have to worry about that at all. Yes? Yeah. Yes, we have homework tonight. All right, so here's another one. Here's a different one. So now here we've got 1/3 as being our base. Okay? So when I take and look at x in the y values, okay, so I'm going to choose the same x values. We'll go -2, we'll go -1, we'll go 0, we'll go 1, and we'll go 2. And let's just start with 0. If I take 1/3, that's a 2. If I go 1/3 and I raise it to the 0 power, okay, now this is a reason why we talked about exponents a couple weeks ago. Okay, doesn't that mean I can take this 1 and raise it to the 0 power, and take that 3 and raise it to the 0 power? And what's 1 raised to the 0? 1. What's 3 raised to the 0? Nope. 1. What's 1 divided by 1? 1. Okay, so if when x is 0, I get 1 back. Okay, now let's try 1/3 raised to the first power. Well, that's 1 raised to the first over 3 raised to the first, which is just 1/3. Okay, let's try it when x is 2. So that gives me 1 squared over 3 squared. What's 1 squared? 1. Oh, what's that all about? So 1 squared is 1. What is 3 squared? 9. So I get 1/9. Is everybody okay with that? Let's do it with the negative values. Let's go. Now if I go 1/3 to the -1, We talked about how that is 1 to the negative first, 1 to the negative first, 3 to the negative first, like that, right? Remember doing that? Do I like negative exponents? So where is this one going to go? To the bottom. Where is this one going to go? To the top. What's 3 over 1 the same as? 3. Okay. Then we do the same thing with that negative 2. So 1/3 raised to the negative 2. So we get 1 to the negative 2 over 3 to the negative 2. What happens to this 1 to the negative 2? Because denominator, what does this one do? Okay, so it gives me 3. So what's 3 squared over 1 squared? 9 over 1, right? Okay, so now, let's look at that graph. If I go negative 2, 9, that point there, and let me just graph, just so it looks cleaner in front of you, I'll graph it on Desmos here. Okay, so we had negative 2, 9. We had negative 1, 3. We had 0, 1. We had 1, 1/3. And we had 2, 1/9, right? If I graph that, okay, so if we connect this with a smooth curve, we get that thing there. Is that okay with everybody? Okay. How does that compare to that one? Good. Say it again. Yes. Okay. So it's a reflection, right? It's a flip. We took the red one and we flip it on the y-axis. Okay. We call it reflect across the y-axis, and it becomes the blue one, right? Does that make sense? And look at the structure of how these two related. How are the base of 3 and the base of 1/3, how are they related to one another? They're what kind of things? Starts with an R. They're reciprocals. Okay? So that's useful. So if I wanted to know, like, what does 1/4 raised to the x look like? Okay? So let me clean this up real quick. If I want to know what 1/4 to the x looks like, maybe I do that first. That's 4 to the x, right? And now think about reflecting that on the y-axis, which basically means this point here is going to stay. That point right there is going to flip to right there. Does that make sense? Okay. Got a couple other nice points here. This point here, it's actually that point right there. It's going to flip to right there. If I go 1/4 raised to the x, you see that exact reflection, right? Okay. Now, let's do something algebraically to see if we can draw a connection, because you're going to see some of these things in your homework. If I have, you guys just told me that we went 1/3 to the x, and you guys were doing that when x was a number, and you were able to tell me that basically if that was 2, it was 1 squared over 3 squared, right? If it was 3, it'd be 1 to the 3rd over 3 to the 3rd, right? Okay, but it's x right now. Okay, and actually let's make it, let's do this. Let's make it negative x. Actually, no, let's do it this way. This is fine. Let's take this and leave it as x. Let's go 1 to the x over 3 to the x. Okay? Now, this is going to seem kind of weird. But I'm going to take this and I'll put it down here in the denominator. What do I need to do to the exponent to put it down there in the denominator? Make it negative. And we'll do the same thing to this. I'll move it to the numerator. So what do I have to do with that exponent? Make it negative. Okay. So now here's where I think it maybe gets kind of weird. is this the same thing as 3 over 1 raised to the negative x? If I wrote it this way, does that, when I distribute that negative x to these exponents in here, does it still give me that right there? Okay, so all these things are equal. All these things are equal. So that thing right there is the same as that one. So 1/3 raised to the x can be rewritten, if we wanted to, as just 3 to the negative x. Those two things are identical. Okay. Now, if you remember, I think this was chapter 4. We talked about things like if I take a graph, let's just take, let's just go like x plus 4 squared. Okay, if I show you that, if I were to go through here and multiply the x just by a negative, let's look at what it does to that graph. So I'm going to take that x and multiply it by a negative and leave everything else the same. What did it do to create that purple graph? What did it do to the green one? Flipped it over the y-axis, right? Okay. Well, what if it was, let's look at a different line. Let's go x to the third. X plus 4 to the third. So that one right there. If I multiply the x by a negative, does it reflect that over the y-axis? Does that make sense? So let's look at f of x equaling 3 to the x. Looking like that, right? Now if I take that x and make it negative, what's it going to do to that black curve? It's going to reflect it over the y-axis, right? Does that make sense? But we already said that if 3 to the x is the black one, then 1 over 3 to the x is that blue one, right? But what are we seeing about the blue one and the red one? They're 100% identical, right? So we have, what I'm trying to get at here is we have options on how we want to write that red or blue one. Okay? And our laws of exponents, this is why we learn laws of exponents. Our laws of exponents allow us to basically realize that even though it's two different looking rules, through the use of laws of exponents, we realize that they are indeed the same rule. Okay? People always ask, why we in algebra, why are we learning things like laws of, like, when am I going to use that? This is where you would use that so you can realize a relationship between something that might be maybe more useful to you in the real world. Because eventually what we're talking about is, how do these curves, how do they work inside story problems? Okay? This black one is called exponential growth. Okay? So populations will increase like that black curve. Okay? This is called exponential decay, this blue one. Okay? And that shows how things maybe die. Okay? Or we talked half-life yesterday. We mentioned that. That's how maybe half-life will be modeled. So it's important to be able to realize this distinction as we move through some later topics. And we'll stop after this. All of our, and we can see this with at least these two so far. Okay, if my base, we call this base here A, right? That 3 was A for our generic formula or a generic equation. It's A to the x, so A is 3. Right here, all of our exponential functions are going to have that point 0, 1. Does that make sense? Every one of them is going to have 0, 1. Okay, when we did 1/3 to the x, it had the point 0, 1, right? Because no matter what, if x is in the exponent, I put a 0 there, it's going to be something raised to 0, and something, by definition, something raised to 0 is always 1. Okay? This number, so when x is 1, isn't that number right there, isn't that the A value? Isn't that Y value the A value? Does that make sense? Okay. This number here, if X is -1, that number right there, that Y value, is 1 over A. Okay. So what I'm trying to get at here, and we can see the same relationship over here, 0, 1. Okay. If A is 1/3, okay, X was 1, we get 1 comma A. We get that ordered pair. Okay. So what I'm trying to demonstrate here is that every exponential parent function has these points: 0, 1, 1 comma A, -1 comma 1 over A. And that's how you're going to remember to graph these things. So if I say f of x equals 7 to the x, you're going to have, and I ask you to graph this quickly. First point you're going to graph is 0, 1. Okay? What is A in this? The base. Okay? So I'm going to have 1 comma that base. So 1 comma 7. And then I'll have -1 comma 1 over 7. And those will be 3 ordered pairs that I can plot to graph that thing, in conjunction with the x-axis being a asymptote. We have those 4 things, and we can graph our exponential. Okay. If you want to write, I kind of like how Maya said this. If you want to remember it as 1 comma base, and then -1 comma 1 over base, maybe that's how you remember what those ordered pairs, how they're configured. Okay. There's an assignment in Math Excel. Most of it right now is just, I think there's like 11 questions. A lot of it is, here is 3 to the x, choose the graph that goes with it. Here is 2 to the x, choose the graph that goes with it. You won't be able to finish it. There's a couple questions on there that we have to talk about tomorrow, but after tomorrow you should be able to finish that initial 7.1 assignment.
Are these how the quadrants are counted? 1, 2, 3, and 4?
No, it starts here with 1,
okay,
and then works that way. So
okay.
1, 2, 3, 4.